Let's do it.
All right, we are live. Let's wait a bit. All right, hello everyone. Welcome to this week's Quirkcast Weekly News. I'm your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, feel free to ask questions during the episode and we'll get to them. So I guess without further ado, let's jump into it. So Tim, I came across this article that talked about the LHC discovering some new particles. There are a few points I wanted to ask you about. One is that LHCb. Is there like an LHCa? I thought there was only one LHC. And then like what's the big deal about these three particles? Will it change physics as we know it?
Yeah,
So yeah.
yeah. Let me just show some of the viewers some of this recent news. Um, it's from here. It's from the CERN website, which is the Center of European Nuclear Physics. It's a very legitimate news, and let me just read you guys the title of this news. It says LHCb discovers three new exotic particles. The collaboration has observed a new kind of pentaquark, in quote, and the first ever pair of tetraquarks, also in quote. And this is indeed quite an exciting news. It's quite an extraordinary discovery, but it might not be the ones that a lot of people are thinking of, right? So I guess we'll spend some time breaking down into that. So at the end of the day, there is an experiment at LHC, the collider. It's one of many. It's one of four, I believe. There may be others, smaller experiments. They discover three new particles, right? But the devil lies in the details. What exactly are those particles? What does that reveal to us? We'll discuss more.
Right. So I guess like you mentioned several things. Pentaquark, tetraquark. First of all, like what is a quark? What the quark is my question to you.
Yeah, Mikey,
Do,
you want to take a stab or?
Oh, what are quarks? Um, Quarks. Okay, yes, I'm kind of split on this article because there's a lot of articles that have been coming out talking about discovered new particle this, discovered new particle that. Um, and after some discussion with Tim today, I think yeah, this is it's a proper title to the article. Yeah, I would say as a particle physicist that yeah, genuinely can say that this is like a true discovery of a particle, but it's different from the discovery of like a what we call a fundamental particle, right? Like people invent new molecules all the time, right? Like people are always combining chemicals in different ways and making new ways of combining things that we knew already existed. Um, and that's exciting. I'm not trying to discount that, but it's not in the same league as like finding a new fundamental component of nature, like a new fundamental component of reality. Um, so we shouldn't look at the title of this and think that, oh, they discovered some new fundamental particle. These are really just different ways of combining particles that we knew already existed, which we call quarks in this case. Um, and yeah, quarks are like one of the particles that, at least for now, look fundamental to us. And there's a very small number of these particles, so they're very special. So finding a new one of these special particles is like extra big news. Finding another way that they can be combined is, it's big news, but don't think that
Yeah,
there's been any kind of like shift in
yeah,
scientific paradigm or anything.
yeah. I guess the name itself is pretty descriptive. Descriptive. Pentaquarks literally is just kind of like a combination of five quarks, and tetraquark is kind of like a combination of four quarks,
Yeah.
right? So that's interesting. These are just new combos, I guess, of quarks because quarks comes in many different flavors, six of them totally, at least for as far as we know, and And yeah, and these new particles, these new combos, should I say, which are legitimately new particles, were discovered by the LHCb experiments, right?
It's actually a lot like discovering a new atom, isn't it? Like if you just think about the process and they say like, oh, they discovered this new element. Really, what they mean is that they made this really heavy atom for like billionth of a second, and then it scattered. But they managed to like hold it together for like a second. It's supposed to, like it's philosophically it's the same as that.
Yeah, I think I agree
I
with that description. It is quite similar to like a discovery of a new element, except element in this way just means combination of quarks. And just to give a little background, right? Things like protons and neutrons are combinations of quarks, and these are two of the combinations that we're familiar with. But for us particle physicists, there are actually many other combinations that are very short lived, but nonetheless we have discovered them. We call them like the particle zoo. They are mesons made of quark and antiquarks. They are baryons it could be made from strange quarks, could be from charm quarks, different types. You can even have three up quark together, and I think you get one of those baryons that could have plus two charges as opposed to plus one charge for a
Delta
proton.
plus plus.
Yeah, there's some pretty strange combinations. Those don't live very long, but those are well known to exist, basically.
They actually
yeah.
fit into like this crazy geometry if you
Right.
plot them.
Wow. So I guess like now before we go too much in the weeds, I want to take a step back and kind of mention one of the words you mentioned, Mikey and Tim, particles. So you mentioned, Mikey, that there are like different kinds of particles. There's fundamental, there's like composite and various things. Like, can you walk us through maybe the history of like how the definition of particles evolved, starting from like way back when Newton was there, and or whatever and just sort of give like the audience kind of a background of that.
Yeah, sure. I think I actually view this as like an existential battle between like two opposing forces. Um, like the reductionist view, and this goes back to like ancient Greek philosophers who, reductionism is the idea that you can understand something best by understanding its constituents, because everything is made of smaller things. And if you understand those smaller things, they tell you how the bigger things work, and you can just understand everything that way. And there's this other camp of people who are like, I would say like the holistic people, people who, anyone who subscribes to like holistic medicine would be in this camp. And those are people who think that you can't describe anything in like a vacuum. It only makes sense to talk about things in terms of like the relationships between other things. And this is like an existential battle going philosophy and physics and like social media, like everywhere. Um, and but I think the reductionists got the jump because Isaac Newton, when he kind of started modeling things as particles, that was like the quickest dumb way to make progress, and he made a tremendous amount of progress, right? Imagining everything was made of tiny, tiny particles and just doing everything the reductionist way. It gave us like all the technology that we know and love today. Um, but then when people started to study like particle physics a little, okay, so we were starting with Newton with the assumption that everything is made of smaller things. It's like a clockwork universe. And then if you're going that way, then the hope is that there's just maybe like a small number of like truly fundamental things like Lego blocks from which everything else is made. And that's like the fantasy of Newton's camp. Um, and so far for the last 300 years, we've been making steady progress on that. And we've whittled it down to like these just 20 or so like basic components that describe everything. And it's like a beautiful tapestry framework. And people are really tied to this idea that these fundamental particles are really special. But there's starting to emerge a lot of evidence for the other camp, and in modern times that, there's actually kind of like a correspondence between these descriptions, and it doesn't really make sense to talk about one or the other in certain situations. And so, oh, sorry. Yeah, so the distinction between fundamental and composite is kind of more obvious and intuitive, right? Like the fundamental stuff is important. The derivative stuff is less important, right? Like everyone, kind of thinks that in some way. I don't know. I think the more interesting thing is like the modern viewpoint that maybe that's not true. Maybe these composite particles are also fundamental in a sense. Um,
Yeah,
I don't know. This article's giving me philosophical pause.
I mean, I guess to simplify it, we can kind of put these different types of particles on a spectrum. I think that's fair. Like from the most fundamental, these are like the quarks, the electrons, or even the Higgs
Wait. I don't
boson.
know. Should we put fundamentalism on a scale? Because like if you actually believe that anything is fundamental, then those things which are truly fundamental have a special status, right?
Well,
There's no.
I mean, I think this is just for like colloquial speech, right? I think physicists have a clear, at least the field right now, have a clear understanding on what we think are fundamental so far versus
Do
what.
we? Uh,
No, I think that's fair. Like for example, like pentaquarks and tetraquarks, we would think that they are probably they're composite. Like they're pretty obviously composite,
in a certain
unquestionably,
description,
right?
they're composite, yeah. But like as we were just discussing, it's kind of it is a continuum.
Yeah. So I mean, and then on the other side of the coin, you can say like water waves. Water waves are definitely composite, but these waves, for example, electron waves inside material, that's definitively kind of composite. The electron is interacting with the the lattice of the atoms, and those turn into what we call quasi particles that are more like waves than they're more like water waves than fundamental particles. So those I would kind of list them on to the other extreme of the spectrum, right? Those for sure are composite, kind of, and like nuclei and these pentaquarks are kind of a little more fundamental, and quarks and electrons are, at least as far as we know, are pretty fundamental, I would say.
So actually, one question I have about that, if we lived in a material where these like electron waves were the only thing we could observe, then we would say these things are fundamental. But because they're not embedded like in the same kind of material that we're embedded in, would you say like that's what gives the distinction between like what is fundamental and what isn't? Essentially kind of like we could think we're in like this substrate and the particles that emerge out of it,
Yeah,
and this reductionist point of view is what would be considered fundamental.
I think, I mean, to some extent, I think this is the conundrum that Mikey is having. Like, if there is a substrate in which we live, and we don't know yet, but then we haven't seen any evidence of it, then yeah, what you said is correct. And all the particles that we have found could be like a little dressed up particle, coming from something more fundamental in combination of the substrate that we live in. That's plausible because, like, if we live in a hunk of metal, the only thing we'll ever know are these emergent electronic waves.
Well, in a sense, that's exactly true, right? We are living in a substrate, like the gravitational field, and everything is kind of a mix of gravity and stuff.
Yeah, I mean, but I don't want to make it that ambiguous. At least there's some ambiguity, but I think the mathematical description would at least right now where the field is, the description that these fundamental particles are fundamental is highly favored because it's convenient. So I would say, like, if you talk to,
Yeah, because everyone's in Newton's camp, because Newton made the most money, and everybody follows the money.
I think that that's a matter of practical standpoint, right? So yeah, from that respect, I would say, yeah, the pentaquarks are definitely not fundamental, right? Like we did not discover three new fundamental particles.
Uh, so are you saying so if we go back to this article talking about discovering three new kinds of particles, they're not three new fundamental particles, but three new composite particles. Am I understanding that correctly?
Yes.
Yeah, I think the thing that makes this exciting from a physicist perspective, which I think is kind of lost on the general population, is that like the theory that describes how the quarks can combine makes very insanely specific predictions. And so far, all of those have come out like exactly as they should. And one of these predictions is that if you combine four of them in just the right way, they'll stick together in this weird configuration for like a billionth of a second. And even that, like very, very obscure, like the most obscurest, the most rarest prediction also holds true. So people were expecting this actually. If we didn't find pentaquarks, that would be more of a scientific discovery than if we did.
Well, I would say it's maybe it's not so clear because I think there
No,
is some
if we had
debate.
a reliable way to produce pentaquarks and we didn't find them, that would be a way bigger discovery than finding them. You can't deny that.
That I'm actually not sure. Well, I
What?
guess
No. The prediction of pentaquarks is that would be a direct violation of QCD prediction.
no. I think
QCD says that pentaquarks can exist. What do you mean?
no. I think it's ambiguous, right? Because QCD quantum chromodynamics is a very hard force to study. Well, let me preface it a little bit. Because these new particles are basically different combinations of quarks, their discovery really doesn't really isn't that it's not that intriguing in terms of new new types of matter that we discover. It's more like a window into understanding how the glue that create these particles work, which is and that glue is an attractive force, and that's quantum chromodynamics. But I think in this regime, quantum chromodynamics in this regime, it's very hard to calculate. So I'm not sure whether pentaquark and tetraquark was a sure thing. I mean,
Well,
either
tetraquarks were. I don't know about pentaquarks, but I studied tetraquarks, and tetraquarks are a pretty sure thing. That
maybe,
um,
yeah. But I mean, their confirmation or their lack of confirmation will tell us something fundamental about these forces, which is quite mysterious, even though we know that they exist very well.
I don't know. Their lack of discovery would have been, if we had a reliable way to discover them, their
Yeah.
lack of discovery would have been more intriguing. I'm gonna stand by that.
But I would still add that while just discovering them is one thing, we also would like to study their property, right? So one of the questions that comes up after the discovery is that these new particles, what do they look like? Are they more like molecules or like more nuclei? Are they more like nuclei, like helium, a bunch of protons bound together? Are they more like that, or are they more like a proton, where a jumble of quarks are just really stuck to one another without too much, like substructure, like chunks. So that's still to be understood. Like, we still don't quite know.
Yeah, I'm not trying to be a jerk, but I mean, I just think like, what's the probability that this is gonna be that like studying the intricate properties of the pentaquark and the tetraquark, like what are the chances that this is gonna lead to like the next big thing? Uh, I wouldn't put my own money on it.
Yeah. So I guess like what I'm hearing from both of you is that this wouldn't this like won't really change the standard model of physics very much, if anything at all.
At all. No, it's the opposite. The standard model of physics predicts this.
Ah, okay. Then so
Yeah,
this
that's
this
why
gets
I was saying
added.
that it would be kind of like a bigger discovery if we should have seen it and we haven't.
Yeah, it's. I
Ah,
guess it's more like this gives us a better understanding of how the standard model of physics describes reality. And
Yeah, but it mostly kind of just shows that everything is working as it should,
yeah,
according to what we expect.
but also theoretical considerations aside, I would say this is also quite a experimental achievement if
Of
you think
course, yeah,
about
there's
it.
no doubting that.
This type of work exemplifies what the LHCb is capable of, which is an extraordinarily impressive machine.
In fact, that's the best distinction. Yeah, this means this is a great achievement experimentally, but it means almost nothing theoretically. That's why it's like hard to bridge the gap.
Yeah. So I guess for this article, would you say this is worth it to read or not?
I mean,
Might
it's a
be
CERN article.
worse.
You can trust everything from CERN.
Yeah, I mean, this is the first source, right? This is like, and in fact,
CERN
it
has quality control.
very, very high quality control. Let me give you that. I have no doubt that this article went through dozens, if not hundreds of physicists to check for accuracy, to make sure there's no misinformation whatsoever.
Yeah.
Um, you know, that,
Anything from CERN, by the way, going forward is,
yeah.
you can pretty much trust it that it's gone through the toughest gauntlet that exists in terms of
Yeah.
quality control.
And
Probably,
yeah, and also these are
information.
large experimental collaborations, right? Hundreds of scientists, experimentalists, and well, and some theorists are working on it.
It's not just the numbers. I've really come to believe that like there's a higher standard for scientific veracity and I mean just like the kinds of sigmas you're willing to allow are much smaller. So nothing's going in CERN.ch unless it's like above 5 sigma. You can bet your bottom dollar on that.
I see. I see. So what you're saying is it's extremely rigorous and is extremely trustworthy
It's
because of what
equivalent
comes
to a
out.
scientific journal. Just if it's on the CERN website, it's like a scientific journal dumbed down. Like they wouldn't allow anything else to like not just any scientific journal, but like the most extremely rigorous scientific journal because there's a lot of variation among scientific journals as I've found recently.
Fair, fair. Any concluding thoughts to leave our audience before we head out?
Read articles from CERN.com. I mean, they don't have big news often, but when they do, I mean, you can at least believe that from a scientific viewpoint, there's a valid way to believe everything they're saying.
Yeah, I would say yeah, definitely go read it. It's interesting, and it also gives you a chance to learn more about the LHCb experiment and really, our theoretical thinking about this discovery is not to undermine the extraordinary experimental achievements. And check check out that article. You can look at the paper. Well, actually, there's no paper yet, but the seminar. There's some very nice plots and statistical analysis that goes into this discovery, and many of which are quite extraordinary. So
Great. So on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
yeah, see you all next week.
Yeah.
Bye bye.
Bye.